So hello everyone again. This is lecture 4 part 3 of current electricity. Today we will move on with a new discussion, that is the resistance in series and parallel. In the last lecture I explained you the concept of electrical energy and power. Today I will move on with the further discussions of currents and how are the resistance in series and parallel are being obtained. So I am Samir Lavankar. Let's begin our discussion. So right now we are on the 10th part, that is the combination of resistors in series and parallel. Before that I explained to you this concept of electrical energy and power. How is the energy loss is being obtained, that is equal to P square into RC upon V square, and finally to reduce that power loss we can just increase the voltage in the transmission cables, and that voltage can be then transformed into the value of steady voltage, which can be directly used into put into good use in our homes. So that was a final concept here. Today we will move on with the further discussions of combination of resistors in series and parallel. Okay. So please look over here carefully. So first of all, the current through a single resistor R across which there is a potential difference V is given by the Ohm's law. We know that I is equal to V by R. Quite evident. It is just the mathematical formulation of changing the concept of dividing the complete equation by R value. We will get I is equal to V by R. Okay. Resistors are sometimes joined together and there are simple rules for calculation of equivalent resistance of such combinations. So finally the complete agenda of this thing is find out the value of R equivalent. Okay. So resistors are sometimes joined together and there are simple rules for calculation of equivalent resistance of such combination. So let us say this is the first combination here, for which we need to find out, we just need to find out the value such that if I make it as a single resistor like this is the current I passing through it, and I write as Req, what will be the function of R1 and R2 here. So this is the complete mathematical formulation which we need to obtain in this complete concept. Similarly for this thing also, if I just need to find out a resistance R equivalent, so that I can change this. Let us say there is a current I passing through it and this will be the R equivalent. What will be the function here of R1, R2, R3. Okay. So two resistors are said to be in series if one end of their end point is joined. That means this point. So this point, as you can see, that end point of this resistor and this resistor are being joined here. Similarly, the end point of this resistor and this resistor are being joined here, and end point of this resistor and this resistor are being joined here. So then we can say that these two resistors here are in series. So these two resistors are in series here, and these three resistors are in series here. Okay. Next thing, if a third resistor is joined with the series combination of the two, then all three are said to be in series. Clearly we can extend its definition to series combination of any number of resistors. Quite evident, we can just add one more resistor here and again add one more resistor here, and hence those 5 resistors can also be said to be in series. Okay. Next is the parallel concept here, that is 2 or more resistors are said to be in parallel if one end of all the resistors is joined together. So as you can see, one end of both the resistors are being joined together. Similarly, I can increase this also like this. I can increase this also here. So these 4 resistors are also said to be in parallel. Okay. So if all the resistors joined together and similarly the other ends joined together. If all the resistors is joined together, as you can see, and the other ends are also joined together. Here also it is joined together and here also it is joined together. Then those resistors are said to be in series. Similarly for this concept also, if we need to find out the combination of resistors, we just need to find an equivalent resistance denoted by R equivalent. If these are the two ends, there is a current I passing through it, let us suppose, then what will be the function of R1 and R2. So this is the thing which we need to obtain. Now let us move on. So now let us move on the derivation of the series of resistors. Okay. So let us consider two resistors R1 and R2 in series. So we can just take this to be an example only for that. Let us consider those R1 and R2 to be in series. Now the charge which leaves R1 must be entering R2, quite evident, because there is a no difference. The complete charge which is being obtained here after some time t will be at here only. So the complete charge movement is occurring from these 2 points here. Okay, so this thing is also being done here. The charge which leaves R1 must be entering R2, quite evident. Now since current measures the rate of flow of charge, this means that the same current I flows through R1 and R2. So this thing is also being done because it is nothing but current is nothing but small q by t. Therefore the current I which is passing through this portion will be same as the current I which is passing through this portion. So this thing is also been explained here. Now next thing is, so by Ohm's law the potential difference across R1 will be nothing but V1 which is equal to IR1. So it is nothing but the simple derivation or simple formulation of Ohm's law, that is potential difference across R1 will be IR1, and similarly potential difference across R2 will be IR2. So nothing to write here, so I will write in the next line here. So next, therefore the potential difference V, so the combination is nothing but the potential difference to 1 and potential difference to 2. Why? Because let us suppose if I draw the cell here, let us say this to be resistance R1, let us say this to be resistance R2. Let us say this is the direction of current flowing. Now if the potential difference across these two portions are V, then that means the potential difference across these two will be capital V, right? Therefore if there is we need to find out the potential difference of these two, then it will be simple addition, because some voltage difference will be obtained across the resistance R1 and some potential difference will be occurring across resistance R2, but the sum of both will be equal to the EMF which is supplied, which is equal to capital V. Therefore the potential difference capital V across the combination is V1 plus V2. So V1 plus V2, and from these equations we can obtain V1 is equal to nothing but I into R1 plus V2 is nothing but I into R2. Capital V I into R1 plus R2. Okay, moving again. Therefore, thus as if in the combination had an equivalent resistance R equivalent, which by Ohm's law is nothing but Req. So Req can be, I just obtained you, it was nothing but a simple resistor like this having a current I, and because a single resistor the voltage difference across these 2 points will be capital V and the resistance will be R equivalent. Therefore R equivalent will be equal to capital V into, sorry, R equivalent will be nothing but the value voltage is given to you and I is given to you. Therefore R equivalent will be nothing but V by I, it will be equal to V by I, and therefore the value of voltage in the previous slide was nothing but I into R1 plus R2 divided by I gets cancelled. Therefore R equivalent is nothing but R1 plus R2. This is the final formulation. Similarly, we can just use this in the process of 3 resistors, 4 resistors and resistors also. So if we had 3 resistors connected in series, and similarly the voltage difference will be nothing but it will be divided into 3 parts, V1, V2 and V3. V1, V2 and V3 will be having the value of formulation which is equal to IR1 plus IR2 plus IR3, because the current is same. Why the current is being same? Because the charges which is passing through resistor R1 will be equal to charges passing through resistors R2 will be equal to the charges processing through resistor R3. Because the charges are same, therefore current will be same, because it is nothing but delta T, Q by delta T only. Therefore the current passing through the resistor R1 will be equal to the current passing through the resistor R2 will be equal to the current passing through the resistor R3. Therefore V is nothing but I R1 plus I R2 plus I R3, which is equal to I into R1 plus R2 plus R3. So R equivalent is nothing but capital V by I, which is equal to I into R1 plus R2 plus R3 by I. Hence, R equivalent is obtained equal to R1 plus R2 plus R3. So what we need, what we found out from the complete formulation, that if there are series of resistors, then the R equivalent will be nothing but the summation of all the resistors which are in series. This obviously can be extended to a series combination of any number n resistors, and the equivalent resistance is nothing but R equivalent is equal to R1 plus R2 plus R3 plus dot 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 till Rn. So this is the final formulation for series of resistors. Let us move on with the combination of resistors now. Okay. Now consider now the parallel combination of two resistors. So we just need, so the final formulation is we need a resistor R equivalent. Let us say the current I is passing through it, the potential difference is V, and the resistance R equivalent is being asked. So how is this R equivalent? A function of R1 and R2. We just need to obtain this. Okay. So this thing is being done. Now the charge that flows in A from the left flows partly through R1 and partly through R2. Quite evident. As you can see, there is a charge distribution here. Some charge will go in this direction, some charge will go in this direction. Therefore, if there is a difference or the partial charge movement, that means that the current is also partially moving in R1 position and R2 position. So the charge that flows in A at A from left flows are partly through R1 and partly through R2. Therefore, the current I1 and I2 shown in the figure are the rates of flow of charge at the points indicated, and hence we obtain that I is equal to I1 plus I2. Therefore, there will be a distribution of currents in both the resistors here. How that distribution is taking place, we will try to obtain this complete concept in subsequent slides in the concept of the Kirchhoff's law, etc. But for now, just let me explain this concept only, that therefore, because there is a reduction, therefore distribution of charges happening in both the resistors, that is R1 and R2, therefore there will be a difference in the currents also. If I denote the current passing through R1 to be I1 and the current passing through R2 to be I2, therefore the total current I will be equal to I1 plus I2. Okay, next is the potential difference between A and B is given by the Ohm's law applied to R1. So capital V, that is potential difference. Please make sure here the potential difference across both will be same, because the ends are same. Okay. So the potential difference between A and B is given by Ohm's law applied to R1, which is equal to V is equal to IR1. Now this thing is been explained, V is equal to IR1. Similarly for the second resistor also, potential difference V equal to nothing but IR2. Here only the thing which is varying is nothing but I, which is equal to I1 plus I2. So using these two as equation number 1, if I just denote it here, I is equal to I1 is nothing but the value of this will be I1 and this will be I2 here, just sorry for this. Okay. Now I1 will be nothing but V by R1, and similarly I2 will be nothing but V by R2. We know that the value of current I can be obtained using value of capital V by R equivalent. So now just dividing or cancelling capital V from both sides, we will get 1 by R equivalent is nothing but 1 by R1 plus 1 by R2, and this is the final formulation for parallel resistors. So when the value of resistors are in series, it is a simple addition, and if the value of resistors, or if the resistors are in parallel, then the formula will be nothing but 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus dot 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 till 1 by Rn. So that is the complete formulation being done for resistors in series also and parallel also. So just let me iterate it, what is written here. So also Ohm's law applied to R2 gives you V is equal to I2 R2. Therefore I is equal to I1 plus I2, which gives you V by R1, V into 1 by R1 plus V into 1 by R2. If the combination was replaced by equivalent resistance R equivalent, then we would have by Ohm's law V is equal to I R equivalent. So it is nothing but V is equal to I R equivalent. So therefore we can get R equivalent is nothing but capital V by I. So using that equation, using that concept here, we will obtain V is equal 1 by R equivalent is equal to 1 by R1 plus 1 by R2, and that is the end of this combination of resistors also. Now just adding that concept in parallel, let us say there are 3 or 4 or n, then it is nothing but as the current is divided into 3 parts here, I1, I2 and I3, and therefore we can obtain 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Similarly, if there are n resistors, we can write it as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus dot 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 till 1 by Rn. So, this is a complete agenda, this is the complete funda of your combination of resistors in series and parallel. Okay. So, this thing is also been explained. Next, this formula for equivalent resistance can be used to find out the current and voltages in more complicated circuits. So, if for example, if we need to find out the value of equivalent resistors for this, so we just need to change this complete resistors here into a simple R equivalent such that there is a current I passing through it and the potential difference is V. So, now how will you do this concept here? So, as you can see that these two resistors are in parallel. Therefore, if we denote this resistors by some resistors R equivalent 2 3, then that will be equal to 1 by R2 plus 1 by R3. Hence, R equivalent 2 3 will be equal to R2 R3 upon R2 plus R3. So, this thing has been obtained here. Now, as these two resistors are in series, therefore, we can write that R equivalent 1 2 3 is equal to R1 plus R equivalent 2 3. Therefore, which we obtain is R equivalent 1 2 3 is equal to R1 plus R2 R3 upon R2 plus R3. Therefore, we can obtain R1 R2 plus R1 R3 plus R2 R3 upon R2 plus R3. So, this is the final equivalent resistance for this series of this combination of resistors here. Okay. So, just let me iterate whatever is written here. So, consider for example, a circuit in the above figure where there are 3 resistors R1, R2 and R3. R2 and R3 are in parallel, quite evident as you can see, because the ends, both ends are being joined. This end has been joined here, this end has been joined here, and hence we can replace them by an equivalent resistance R23 equivalent, which is between point B and point C, as 1 by R equivalent is equal to 1 by R2 plus 1 by R3. Therefore, we can find that R23 equivalent is nothing but R2 R3 upon R2 plus R3. Now, the circuit now has R1 and R23 equivalent in series, as you can see here, and hence their combination can be replaced by an equivalent resistance R123 equivalent equal to R123 equivalent, which is equal to R23 equivalent plus R1, as it is in series. So, I think that formulation is not given, that formulation is also given. Therefore, if the voltage between A and C is V, therefore, the current I is given by I is equal to V by R equivalent, and therefore, we can obtain that the resistors value is equal to R2 plus R3 upon R1 R2 plus R1 R3 plus R2 R3. And hence that is the end of combination of resistors in series and parallel. So, finally, what we obtained is if the two resistors are in series, then it is nothing but the R equivalent is nothing but R1 plus R2, and if the resistors are in parallel, if we obtain it for n resistors, it is nothing but the addition in all this form, and if the resistors are in parallel, let us say this is in series, this is in parallel, it is nothing but 1 by R equivalent P is nothing but 1 by R1 plus 1 by R2 plus dot 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 till 1 by Rn. Okay, so this is the complete end of your combination resistors also in series and parallel. So, let me stop it here only. In the next lecture, I will start with the concept called as cells, EMF, internal resistance, so on. What is EMF will be explained in the subsequent slides in this concept here. Okay. So, the course progress for you. So, the first concept was we started with the introduction concept, then we went on to electric current, that is Q by T, and the mathematical formulation in infinitesimal method, that is limit delta T tending to 0 del Q upon del T. Then the electric current in conductors, we understood the concept of different conductors, what happens when the charges are being free in nature or bounded in nature. So, we understood 3 different things, that is conductors, semiconductors and insulators. And in Ohm's law, we understood the concept of V is equal to IR and R is equal to rho L by A. Then the drift of electrons, we understood the concept of Vd and how that concept of original resistivity came into picture using the concept of conductivity, and the reciprocal of conductivity is nothing but the resistivity. Then the limitations of Ohm law, we understood 3 different formulations of how the limitations happen and 2 devices such as diodes and gallium arsenide. In the resistivity of various materials, we understood 2 different types of resistors which are happening. In the carbon resistor, we understood the concept of color coding of these resistors. And the temperature dependent resistivity, and we understood the concept of how the increase or decrease in temperature changes the resistivity in conductors, semiconductors and insulators. That the change in the conductors is different from that of conductors, semiconductors and insulators. Then the electrical energy in power, we understood the concept of how are the transmission or the power loss is happening when the current is passing through point A to point B, and how we try to reduce it in the subsequent surroundings. And finally, in this last lecture here, we completed the concept of combination of resistors in series and parallel. In the next lecture, we will start with the concept of cells, EMF and internal resistance, then cells in series and parallel, followed by Kirchhoff's law, and then the final, the complete applications of Wheatstone bridge, meter bridge and so on. So let me stop it here only. Thank you.